So in example 1, we're going to calculate the average force exerted on a tennis ball by Venus Williams' racket. During the 2007 French Open, Venus Williams hit the fastest recorded serve in a Premier Women's match, reaching a speed of 58 meters per second. Let's solve for the average force she exerted on the tennis ball, or her racket did, given the tennis ball's mass of 0.057 kilograms. We'll assume that the ball's speed just after impact was 58 meters per second, and the initial horizontal velocity is negligible. In other words, we don't need to consider the fact that the ball might have been moving horizontally before the fact. It's just a serve. And that the ball remained in contact with the racket for 5 milliseconds. That's important. Well, if we're looking for the average force on the tennis ball, and we have information about the speed and mass, it'll make sense here to apply our idea of impulse, a change in momentum, and how it relates to net force and time, as we saw before. I'll write the expression here once again. All right, so we're just looking for this net force. In this case, there's only one force. It's from her racket. And we are looking for the net force. That means that we need to know the change in momentum, and we need to know the time. Right? If we can get both of those things, then we can solve for the net force. I strongly recommend using a momentum table, at least at first, to help solve problems like this, just to keep track of what's happening before and after the scenario as a way of solving problems a bit easier. Here, you'll notice that we can solve for delta P using our table. That's that last column of our table, and we're given the time. And so we'll use the table to solve for delta P, and then we'll plug in our time and delta P to solve for our net force. In this problem, we can define our initial state as right before Venus hit the ball. And so Venus has thrown the ball up in the air. The ball doesn't have any horizontal velocity. We're only considering the horizontal velocity of the ball in this problem. And therefore, the momentum of the ball before the collision is going to be 0, right? It's not moving before the collision. Now, immediately after the collision, we are given the velocity of the ball, and we have the mass of the ball. So if I multiply those two items together, that will be 0.057 kilograms multiplied by 58 meters per second, and that is equal to 3.306 units of momentum after the collision. And so I know that if the tennis ball didn't have any momentum before, and now it has 3.306 units, I know that the momentum change is just going to be that positive 3.306. That's going to be in kilograms multiplied by meters per second. So now that I've solved for delta P, I'll rearrange my expression here, my impulse expression, looking for the net force. I'll divide both sides by delta T here. That'll be delta P over delta T. In other words, the change in momentum over the impact time, the collision time. That will be equal to 3.306 kilogram times meter per second divided by 5 milliseconds. And I want to make a point here that if you don't convert your units, you should see that the seconds and the milliseconds do not go away. So we need to convert 5 milliseconds first to seconds before we finish this problem. Well, 5 milliseconds, there are 1,000 milliseconds in 1 second. So I can actually just say that if I divide 5 by 1,000, that would be 5 times 10 to the minus 3 seconds. If you don't believe me, you can also do a little bit of dimensional analysis. 5 milliseconds, if we were to go from 1,000 milliseconds to 1 second, you divide 5 by 1,000, you will get 0.005. In other words, if you multiply by scientific notation, that would be 3 decimal places to the left. So you can either say 0.005 here, seconds, or 5 times 10 to the minus 3 seconds. Either one works just fine. Plugging that in, you will get a net force of 661.2 newtons. So that is the average force that Venus Williams' racket exerted on the tennis ball during her serve. All right, let's take a look at another example.